Alright, so now we're going to go to part D of this practice titration, which is at the equivalence point. So whether it's a strong titration, weak acid, strong base, or strong base, weak acid, the idea of the equivalence point, as long as they're both monochromatic, is that the moles of acid added equals the moles of base that we originally had. So let's figure out what that is so we can actually figure out what the equivalence point volume is, because that's going to be important later on. So for the base, we initially had 0.02 liters, 20 milliliters. Got a concentration of a 1/10 mole per liter. Which means that we had 2 millimoles, or 2 times 10 to the negative 3 moles of the trimethylamine. All right, so that tells us how much acid that we need, so that we also need two times 10 to the negative 3 millimoles of that. And so now we need to figure out what volume of acid contains that. So remember that concentration times volume equals amount. So we can rearrange that to say that the volume that we need is equal to the amount divided by the concentration that we have. So so we need 2 times 10 to the negative 3 moles of the strong acid, hydronium. It's going to be, it has a concentration of a 1/10 mole per liter, and that is going to give us a volume of 0.02 liters, or 20 milliliters, which you may have guessed already because the base and the acid were the same concentration, so it shouldn't be surprising that you need equal volumes of each to get an equal amount of each. So this is important. So the volume of our solution at the equivalence point is going to be the initial 20 milliliter aliquot of the trimethylamine plus the 20 milliliters of the acid solution that we added for a grand total of 40 milliliters of solution. Now this is important. All right, so again, what was the reaction that happened here? So we were taking the weak base trimethylamine, reacting it with the strong acid hydronium. So since we have one member of that pair is strong, we can assume a complete reaction. To make trimethylammonium and water. Now, at this point, if we want to build a reaction table, in amount, what would this look like? Well, before they react, you'd have 2 times 10 to the negative 3 millimoles of the trimethylamine. You have also 2 millimoles of the hydronium. We can pretend no trimethylammonium and no water. So in this case, depending on your philosophical bent, they are either both limiting reactants or neither is a limiting reactant. The end result is that they will both lose 2 millimoles. resulting in concentrations of 0 for those guys of both. So we added just enough hydronium to react with all of the trimethylamine and no more. And we will have, in the case of doing that, produced 2 millimoles of the trimethylammonium solution. Now, you can't use the Henderson-Hasselbalch equation at the equivalence point to calculate the solution pH because you don't have a buffer anymore. You are now completely devoid of any large amount of the trimethylamine. So the way that you calculate the endpoint pH is a little bit different. And what you have to understand is that this trimethylammonium is a weak acid. It's the conjugate acid of the weak base. And it's the only acidic species there, so it's actually going to really dominate what the pH is. So from there on in, we need to basically treat this as a weak acid equilibrium based on this concentration of trimethylammonium. And so we have two millimoles of the trimethylammonium contained in 0.4 liters of solution. So this concentration at the end point is going to be half molar. And we're going to use that as the initial concentration of our equilibrium calculation for the Ka of the trimethylammonium. So let's do that. So at the equivalence point, the trimethylammonium is really the only species there that's either appreciably acidic or basic, so it's going to really much determine what the solution pH is. So that equilibrium is simply the weak acid, the trimethylammonium, donating a proton to the strongest available base, which now is just water. And since that's a weak species, this is really an equilibrium. So that's going to reform a small amount of the trimethylamine and some hydronium. And as we just said, from an equilibrium standpoint, we initially had 0.05 molar trimethylammonium. Water doesn't affect the equilibrium. We'll say no trimethylamine and no hydronium. So, since we are devoid of the trimethylamine or the hydronium, we can expect some to reform at the expense of the trimethylammonium, since everything here is 1-to-1. So, once equilibrium is achieved, we will have 0.5 minus X molar trimethylammonium, X molar trimethylamine, and X molar hydronium. So this is the Ka equilibrium for trimethylamine, which means it's going to be, or trimethylammonium, I'm sorry. So it's going to be equal to the concentration of the conjugate base, the trimethylammonium, times the hydronium concentration divided by the weak acid concentration, which is just the trimethylammonium. And symbolically, this is going to solve to x2 minus 0.0500 minus x. Now the Ka for this was pretty small, so we can get by with assuming that this is just going to be x squared over 0.05. And numerically, in a previous problem, we discovered that Ka was 1.9 times 10 to the negative 11. So solving for that, x in this case happens to be equal to the hydronium concentration as well as the trimethylamine concentration. And that ends up being 9.81 times 10 to the negative 7. And so that's going to correspond to a pH of about 6.01. Now, does that make sense? Well, we've titrated a weak base and in the process made a weak acid. That's all we have here at the equivalence point, so the pH is going to be dominated by that weak acid. So we expect it to be a little bit less than 7, and it is. So that looks good.